All right, then. So today we have two things to do. We have to finish up our reviewing. So let me get that open. Yes, there's four more questions left. So this will become part 5 when you look at the Moodle for the solutions. Remember, yesterday I had to break it up into pieces because it was too big of a document. Okay, so today we'll add to that. It'll be part 5. And then you'll be completely ready. I'll post the midterm, which you can hand in. I think we agreed to next Wednesday. Does that sound right? Let's go look at Moodle for a second. I know I made an announcement. Let's see, where could that thing be? Oh, here we are. Yeah. Okay, so let's look at the announcements. Oh, next Wednesday. Okay, that sounds fine. It's a full week. I mean, the exam is fairly long, but I mean, if you've got a week, especially with all your notes and materials, it shouldn't be that bad. So yes, so it does say that here. Good, good, good. No, that's sample midterm, sorry. Oh no, it's yeah, it does say it here. Perfect. Yes, Wednesday the 30th. That would be fine. Okay. And it's pretty much exactly what we've just been doing. In other words, the sample midterm and the actual midterm are very, very similar to each other. Very, very similar, as a matter of fact. So I don't think you'll have any trouble with it at all. And as usual, now here's something that we do run into occasionally. If you are taking a lot of pictures of these documents, sometimes space can be a problem with emails. What you should probably do is just send them one at a time. People sometimes write to me and say, "Oh, I tried to send my work, but it wouldn't go through." The first thing you should always try then is to just take each document or each photo and send it one at a time. That should take care of it because the pictures are fairly bulky, but if you only do it one at a time, that should not be a problem. If it is, we might be able to use Google Drive or something like that. I'm not really that on top of the technology, but I know that it can be done. Okay, so since this is a fairly lengthy document, you might run into a problem with the memory requirements of Gmail. So if you are having a problem, just let me know. Okay, we'll figure it out. I'm not going to penalize anybody because the technology doesn't work. That's for sure. Now, also, it seems hard to believe next week is our last week. I just want to remind everyone that next week we have to change the time because one of my other schools kind of threw me a curveball. So I'll remind you again with my announcements, but next week we'll be doing, instead of our usual time, we'll be doing 9 a.m. to 10:30, just because that's what happened to my schedule. So I know it's inconvenient, but we'll get the work done. And if you just can't make it by 9, you can always watch the recordings, which, I'm sure you're aware, they're all on YouTube. Which, in fact, why don't we go visit them right now? We'll take a look at YouTube. And we have, right here is my account. And here's the playlists. And voila, there it is. View full playlist. All of them are there. I'm completely caught up. And, you can feel free to watch these anytime you need to. Just download it and watch it like any other video. Other than that, that's all you need to know. But if you're, since I'm already in my account, if you can't find it, if you just go to YouTube, I think the way it works is that if you go in here and type my name, I think it'll come up. Yeah, that right there. See that? That tells you that you're in my area. And then, I didn't even know this was happening. Now, ironically enough, as you can probably imagine, my name is not all that uncommon. So don't get confused. I'm not a basketball player. I'm not on the Nets. That's not me. If only. And there's probably tons of others as well. No. It should be pretty obvious that we're talking about statistics here. So there they are. All right. So that's that. Also, even though it might be a nuisance, I think we do still need to do one or two more problem sets. It's really more for the practice than anything else. The final is based exclusively on chapters 8, 9, and 10. We're completely done with 8. We're about to do 9. We'll do 10 next week. So there will be a problem set for chapters 8 and 9. which I would like you to have ready by Monday, the way we always do. And then that will be the end of all the assignments. Plus, then you'll have the midterm that week. And then the following week, I believe, you should be able to hand in the final. That one I can check out. The final will be shorter than the midterm because it only has 3 chapters, although they're more complex chapters. The time required to do them, the final exam that is, should be less than the midterm. So, all right, I guess that's everything we needed to go over. And so let's get back to where we were with the last 4 problems on our sample midterm. And as I started to say last time, this first question here, number 11, is actually a Poisson problem. All right, how can you tell? Let's take a look at it. So on average, 3 customers enter a bank per hour. All right, so already you know what's going on here. That tells us that this is Poisson because it refers to events, meaning the customers entering the bank per hour. Okay, 3 per hour. So you not only know that this is a Poisson problem, but you also know that the value of lambda equals 3. And of course, with Poisson, that's the most important detail, lambda. All right. So compute the probability that no customers will enter the bank during the next hour. Now, again, like we did the other day, yesterday, we can do this in 2 different ways. We can use the formulas, or we can use our calculators. That's entirely up to you. All right. So if you did this with a formula, how would that work? All right. So the formula is okay. So in our case, lambda equals 3. And in part A, x equals 0 because they're trying to find out the probability that no customers enter the bank over the coming hour. Okay, so the probability that x equals 0 is e to the minus 3, 3 to the 0 over 0 factorial. Now, if you notice, these 2 terms, 3 to the 0 power and 0 factorial, are both 1s. So basically what you have here is e to the minus 3 power, and that's approximately equal to, oops, 0.04978, let's say, or 79. That's close enough, 0.0498. Now with the calculator, what you're doing is, as usual, second vars, Poisson PDF, make sure it's PDF. This is not a less than or equal to problem. And when you get to that menu, second Poisson is way down at the bottom here. It's C actually. So the first thing they'll ask you for is lambda. And of course, in this case, that's 3. The x value is 0. And then you go ahead and enter that information. And it's the same thing, 0.04978 or 0.0498. That's fine. Okay. Perfect. So let's see what part B is. How about the probability that 1 customer will enter the bank? So the only thing that changes here is the value of x. Okay, so in fact, let's see if I can copy that. Oops, hold on. Now let's just do it directly. Lambda stays 3, but now x equals 1. All right. Okay, so you can see that the right-hand side of this expression is 3 to the first, or 3. This is equal to 3e to the minus 3. So that means it's just triple what we had a minute ago. So if you multiply that by 3, you'll get 0.1494, let's say. All right. And then for the calculator, we only have to change one thing. That would be the value of x. Change that to a 1. And you'll get the new answer will be yep, 1494. Perfect. Okay. Now for C, this one's a little bit different because what's happening is they're asking us for the probability that 2 or 3 customers enter the bank during the next hour. So they're asking us for this. All right, so that means we have to do 2 probabilities and add them up. All right, so when you see the word or like that, it means you're adding 2 mutually exclusive probabilities together, because you're technically doing a union here. You could think of this as, let's say x equals 2 union x equals 3, and then you're combining them. So, all right, so remember lambda is 3. So we have e to the minus lambda, lambda to the x over x factorial, which is e to the minus 3 times 9 halves. All right, and so let's see what that is. It's approximately 0.2240. And then for 3, now here's an interesting result. This is actually 27 over 6, which is the same as 9 halves. So you've also got here 4.5 e to the 3rd power. And so both of them are the same. So in other words, the probability that x equals 2 plus x equals 3 equals 0.2240 plus 0.2240, which is of course 4480. So this does happen quite a bit with the Poisson probability distribution. You do often have 2 probabilities that are the same. It's because of the way the formula is written. Now, of course, we can do the same thing with our calculators. But again, we have to do this twice. Okay, there's no getting around that part of it. All right, so how would that look? Let's try. So this is 2 and 3. So for 2, you'd have 2240, and then for 3, also 2240. So therefore, the probability of x equal 2 plus x equals 3 is 0.2240 plus 0.2240 equals 4480. So any way you look at it, the answer is 0.4480, approximately, of course. All right, now for the rest of this question, we're looking at the moments of the Poisson distribution. The expected number of customers, EX, equals lambda equals 3. The variance also equals lambda equals 3. And then finally, the standard deviation radical 3, which is approximately 1.73 rather. Let's say 1.732. All right, now we've got some standard normal probabilities here. And again, there's a couple of things we can do. The first one, for example, is a bit of a trick question because we're looking at the probability that z is greater than or equal to 0. Which is the mean of the distribution. And by definition, this is just equal to 1/2. If you want to use the tables, what you can do is say, all right, this is not on the table, but what you can do is rewrite it as 1 minus the probability that z is less than or equal to 0, and that is on the table. And that's equal to 0.5. Okay, so let me just go get the tables and prove it. All right, they're here somewhere. Okay, so this one I actually still have it circled from the last time. 0 combined with 0 gives us 1/2. So the probability that z is less than or equal to 0 is just 1/2. Okay, so therefore the area to the right of that is also 1/2 because of the symmetry of the distribution. So using the calculator, you'll do second VARS as usual, but choose norm CDF because it's a continuous distribution. We always use CDF, or at least we will always in this class. And then it's going to ask you for lower, 0, upper. So remember, this is positive infinity. We'll write that as second comma 99. And the default values for mu and sigma are 0 and 1. So in other words, it assumes, unless you tell it otherwise, that you're referring to the standard normal distribution, which is not a terrible assumption. And you'll get the same thing. Now, remember, this is the one where you're getting like 4,99999, this kind of thing. So remember, that's just a rounding issue because we're not putting in true infinity here. So you can round it to 0.5. Okay, great. Now let's see what's coming next. B, less than or equal to negative 1.80. All right, so this is easy to get on the table. All right, so we'll go to the negative table. Let's see, right here, negative 1.88. Works out to be 0.0301. And of course, with the calculator, we should get a very similar answer. This time, the lower limit. This is, of course, the area from negative infinity up to, down to negative, it's negative 1.88 down to negative infinity. Okay, so therefore, here we'll have for a lower limit, negative second comma 99, or negative infinity. The upper is negative 1.88. And the mean of standard deviation won't change. This is still the standard normal. And it's the same. It's slightly different. It's rounded a little bit differently, 0.03005 actually, but we'll round that to 0.01. Okay. So in all of these cases, you're doing basically the same thing, except that if you're using the tables, you often may find yourself having to manipulate the probability to get it into a more convenient form. With the calculator, it's already there. It can do anything you need. So here's another good example of this. Greater than negative 1.36. This is not on the table, the way it's written. So in using the table, what we can do is just rewrite this as 1 minus the probability of being less than or equal to negative 1.36. And that is on the table, the negative table, that is. And the comma is directly above the 7 key. If you're having trouble finding it, if you look directly above the 7, it's there. Yeah, I don't know why they sneaked it all the way up there on the top. They just did. Yeah, it's up there. Okay. Yes, so let's do the calculator now. Oh, no, before we still need the negative 1.36, which is negative 1.3, 0.06, 0.0869. Now, of course, don't forget, that's not your answer. You have to subtract that from 1. Oops. Wait, what did I do here? No, sorry. No, I got it. Okay, we're good. We're good. It's 0.9131. All right, you can see that this is a large area because it takes up most of the distribution. So that whole shaded region is 0.9131. Okay, we're good. And the calculator, of course, will do this directly. No adjustments are needed. This time, what is it? Everything from negative 1.36 up to positive infinity. And of course, 0 and 1 for the standard deviation and the mean. So let's plug that in. Negative 1.36 up to positive infinity will give us 0.9131. Yeah, no, that's it. It's perfect. Okay. And then this is an in-between problem. Now remember, when you're doing this with the table, let's sneak this down here. What you have to do with the table is rewrite that as z is less than or equal to negative 0.53 minus z is less than or equal to negative 1.87. Okay. So in other words, if you look at the graph, you'll see why. So you're basically taking this area and subtracting this area. And what's left over is what you're looking for. Okay, so based on the chart, negative 0.53. We start with negative 0.5. And we have the 0.03, which is up here somewhere. .2981. And then negative 1.87 is up here further. Okay, at their intersection, we have 0.0307. And so when you subtract those, it's 0.2674. All right. Now, of course, we can use the calculator very quickly and easily. So the lower is negative 1.87. The upper is negative 0.53. All right. So we'll plug these into the calculator. .2673. It's slightly, this time it is slightly different. That's because of the rounding. When we calculated, the tables, whenever you use tables, there's always a chance of some slight rounding issues, but that's close enough. That's plenty. Okay. So what do we have? Oh, okay, here we go. So these are normal probabilities. The difference here is that they're not standard normal. Okay, so that means if we're going to use the tables, we have to make some adjustments. What do I mean by that? This is when we get to use that formula. Ah, that one. Okay, so first of all, we're told that the return to this fund's global growth fund is normal. The mean is 12%. And the standard deviation is 30%. So let's convert those into decimals, of course. And we're going to calculate some probabilities. So for A, if we want to know the probability that X is less than or equal to 12%, we can apply this formula. And we're taking the 12 that we started out with, we subtract the mean of 12, divide by that standard deviation of 0.30. So this is the equivalent of asking, what is the probability that Z is less than or equal to 0? So guess what? We know that one. It's a half. All right, so that was a bit of a trick question. And, certainly if you go to the table, you'll see it right there on the top. That one right there, yeah. But if we use the calculator, look how quick this is. What we're going to do is ask for less than or equal to 12. We'll keep all the numbers in the same units as the data we have here. So we have negative infinity. Up to positive 0.12. But now we have to be careful. The mean is 0.12 now. It's not 0 any longer. And the standard deviation is 0.30. It is no longer 1 rather. So let's plug these in. So we're going from second infinity to 0.12. And it's 0.5. Now you notice that there's a very slight rounding. This time, for some reason, it's rounded in the other direction. It's like a bunch of zeros and then a 5. So we'll just call that 0.5. Okay. For part B, we're looking at more than 27%. Okay. Okay. So I'm going to convert this by subtracting the mean of 0.12 and dividing by the standard deviation of 0.30. Okay, so this is the probability that Z is greater than or equal to 0.15 over 30. This is 0.5. Okay, so if you do the calculations, 0.5. And now we can go to the table by rewriting this as 1 minus P is the probability that Z is less than or equal to 0.50. So we go to the table, and here it is. I'll tell you, let me erase these old ones. There we go. The combination of 0.5 and 00, we have 0.6915. And so we're subtracting that from 1, and so we end up with 0.3085. And we're done, unless we choose to use the calculator. Where we just plug everything in directly. So in other words, the lower limit will be 0.27. Oops. The upper limit is positive infinity. And when you do the plugging in, it should be the same thing, okay? $3,085, that's it, perfect. Nice, okay. Part C, less than negative 3%. A little tricky there. All right, let's do this. Okay, so using the tables, we'll convert this into the standard normal form. Whoops, wait a minute. No, this is the X, sorry. Okay, so it's minus 0.03 minus 12. 0.12 is the mean. And then we divide by 0.30. So this is actually the probability that Z is less than or equal to negative 0.5. Okay. And now we can easily look up on the negative table. All right, so let's go look at it. The negative table, get rid of these. Negative 0.5 is down here somewhere. Here it is, 0.3085. All right, so now, of course, with the calculator, we will use the original values, negative 0.03 down to negative infinity. And we should get the same thing. All right, let me just double check it. And we're good. By the way, here's a little helpful hint. Sometimes this shows up in these questions. If you notice that the answer we just got is the same as we got for part B, and it's not a coincidence. Greater than 27%, less than negative 3%. What just happened here is that the symmetry of the distribution tells us that this should be true. because you can see that the this is 15% above the mean, or half a standard deviation. And this is 15% below the mean, or half a standard deviation. So it stands to reason that they'll both have the same areas, and they do. So that's why that happened. It wasn't just a coincidence. All right, are there any more? Let's see. Yes, there's a couple more in-betweeners here. All right. So with the center or mean of 0.12, this is the area between negative point. This will cover just about the entire area. Whatever this is what we're looking for. So again, using the table, we're going to set it up as the probability that is between these two, 0.4, negative 0. Positive 0.42 less than equal to x minus negative 0.18 less equal to x. So then we have to of course, convert them into the standard normal form. Actually, I'll tell you what, why don't we do it this way? Instead of doing this in 2 steps, we'll do the conversion first, and then we'll subtract them. I think it'll be easier that way. So let's try that. The probability and we're applying, remember, the formula is x minus mu over sigma, which in this case is x minus 0.12 over 0.30. And so now we've got okay, so this actually turns out to be -1 up to positive 1. Yeah, that's right. All right, well, I guess it's not going to cover as much as I showed in this graph, but still, maybe I'll fix that a little. It's a little bit deceiving the way I've written it. Sometimes it's hard to tell just by looking at the numbers until you convert them into the standard normal form. Then I just realized all we've got here is the area within 1 standard deviation of the mean. Which you might recall is approximately 68%. So when we get our answer, it should be something like that. All right, now we can do that subtraction business. And these can both be looked up directly in the tables. For positive 1, we have right here 8413. And for -1, that would be this one, 0.1587. So the difference between the two, 0.6826. Yes, this is exactly what we were expecting. All right. And now, of course, we'll try the calculator. The calculator will be easy because it's an in-between. We don't have to deal with infinity. All right, so just change this to negative 0.18 up to positive 0.42. And just confirm that that's equal to 6826. Okay. Oh, wait, I did something wrong. Okay, yeah, it's 68, 26, 27. It's almost exactly the same, except for maybe rounding. All right, and then finally, there's one more. By now, you are experts in the normal distribution, that's for sure. So we'll do everything between -3 and positive 27%. Okay. All right. All right, so the mean is at 0.12 still. Okay, this is what we're looking for. So, all right, so we're after this. And then we'll convert that to the standard normal form. Okay, so this first one, this is actually -0.5. And the second one is +0.5. So what we're looking for is the area within 1/2 of a standard deviation of the mean. And then, of course, we subtract one from the other. And if we look at the table, we can find both of these. Positive 0.5. Oh, it's right there, 0.6915. We had this earlier. And -0.5. No, we had that one before too, 0.3085. Okay. 0.383. All right, now, one last normal calculation here. We've got the calculator. We're looking for the area between. Is it -0.03 and positive 0.27? All right. All right, nothing else changes. Throw that in there, and we'll get .3829. Okay, it's almost exactly the same. It's slightly off. All right. So those are the straight ahead calculations. Now what needs to be done is this Normal approximation of the binomial. All right, so this one has several steps involved, but it all ultimately comes down to normal probabilities. We're taking a binomial distribution. Here, for example, you'll see that we're flipping a coin 1,000 times, and X is defined as the number of heads. So clearly you can see that we could, in principle, do this with a binomial distribution, but it would take a very long time. So instead, we're going to use our normal approximation. Normally, the way we start out is with the 3 moments. Okay, we're going to need them in our calculations. All right, so how does that work? The expected value of X and pi, 1,000 times a half. And by the way, pi is a half because the probability of getting ahead is 1/2, and n is 1,000 because we're flipping the coin 1,000 times. The variance just has that one extra term, but in this case, 1 minus a half is also a half. And of course, the standard deviation is simply the square root. And the square root of 250 is approximately 15.81. Okay, now we get to do some probabilities. So part D, the probability that we'll get between 480 and 520 heads. So the first step is the continuity correction. All right, so what we have to do is widen the interval by adding 0.5 to the upper limit. Unless it is infinity, then you don't bother. And subtract a half from the lower limit. And again, unless it is negative infinity, then there's no point. Okay, so that means here, after applying this technique, we'll have, okay, probability of 479.5 less than or equal to X less than or equal to 520.5. Now, this next step is to convert to a standard normal random variable. And the formula is now now this is no different than the formula that we're used to seeing. What's different though is the way we calculate the mean and the standard deviation. Okay, so in this case, we've already determined that the mean is 500 and the standard deviation is approximately 15.81. So that's what we're going to do right now. So we can rewrite this as the probability of 479.5 minus 500 over 15.81 being less than or equal to z, which in turn is less than or equal to 520.5 minus 500. Okay, so that is equivalent to, let's see, that's about negative, it's almost exactly negative 1.3. All right, that's close enough. Remember, this is an approximation anyway. All right, yeah, it's within plus or minus 1.30 standard deviations of the mean. And so we're going to have the difference between the two. Okay, so we'll go to the tables. Okay, 1.3. 0.9032. And then negative 1.3. .0968. Okay. And the difference is 0.8064. All right. Now, could we have done this with the calculator? Yes. Okay. How would we have done that? So the lower and upper limits would be taken from this continuity correction, 479.5. Up to 520.5. And now this time, though, the mean and standard deviation are these two numbers, the 515.81. All right, so I'm going to throw these into my calculator. Now, in a case like this, there can be some fairly significant rounding differences, but let's just check this out. 479.5 up to 520.5, 515.81, 0.805. Yeah, it's off a little bit, 8052. It's not that far. But there's a lot of rounding that can potentially takes place in this type of situation. And so you shouldn't be surprised to see that it's off a little bit. Either one of those answers is fine. All right, that was that. Now the next one is more than 525 heads. Okay, so nothing's changed, except when you do the continuity correction, let's see. First, you should rewrite this. It's a little bit confusing the way it's written there. The 525 is actually the lower limit. Now, technically, what you're doing here, you could write it in a couple of different ways. Because these are coin flips, you can't actually go above 1,000, but let's just keep it at infinity to be consistent. And then with the continuity correction, yeah, we've seen this before. You theoretically can't do that, but we've seen that it doesn't make any difference because that's the part of the tail that has a zero, almost a zero area anyway. So let's do it this way. Let's call that 524.5 up to infinity. Or you don't even have to write the infinity. In fact, let's just leave that out for now. This is what we really need. And so what we're going to do is convert this. It's understood that the upper limit is infinity when we convert it to the standard normal form anyway. So we're going to have 524.5 minus 500 over 1581. All right, so this is about equal to 24.5 over 15.81. It's about 1.55. Or if you want, it might be easier to write this as z greater than or equal to 1.55, because that's what we're interested in. Everything above 1.55. So now, as far as calculating this from the tables, you recall that we have to rewrite this as 1 minus the probability that z is less than or equal to 1.55. So we can look that up in the table. The positive table, that is. 1.55, 1.5 combined with 0.05 brings us to 0.9394. It's about 0.0606. All right. Now, with the calculator, going back to the beginning, the lower limit we saw was 524.5. The upper limit is positive infinity. And so let's see what that gives us. And you can expect a little bit of a rounding difference. .606. Oh, what do you know? It's exactly the same. Doesn't always work out that way. All right, so finally, at long last, we're at the last part of this review. Part E, or F, whatever it is, F, less than 485 heads. All right. So with this one, we're adding to the upper limit. We're not going to bother with the lower limit because it's infinity. And so then we convert to z. So we'll end up with z less than or equal to negative 0.92. All right, so let's see what that is. Now that one we can look it up directly in the table, the negative table. And so let's see what that is. Oh, wait, sorry, I'm in the wrong one. I need the negative table. Negative 0.92, 0.1788. All right, now, once again, what do we do about this with the calculator? All right, let's see how that works. So remember, this time we're after fewer than 485 heads, which with the continuity correction became 485.5. Okay, so let's see how that turned out. .1795. So it's a little bit different, but again, that's not unusual with these with this technique. It's more than what we're used to seeing, but again, because there's several points at which we're actually rounding. So at long last, this is done. This is the part 5 of our solutions. So I'm going to post these right now. There's no point in waiting. While we're at it, I might as well post the midterm. Hold on one second. I have it right here. All right, let's see. Hold on. This, of course, this eliminates the risk that I could forget about this. And that's why I like to do it right now. All right, so we need the solutions to part 5. And this will go in now. And the midterm can now officially go up there. The real thing. There you go. All right, now after the break, we're going to stop right here for the break. We're going to do chapter 9. We're going to start chapter 9. Now, since this took longer than I thought, I don't think we'll have time to finish 9 today. So what I'd like us to do then, and let me make an announcement about this. Well, first of all, a quick reminder. Might as well throw in a reminder. The midterm has been posted on Moodle. Be sure to have it ready by Wednesday, June 30th. I'll tell you what, since it's long, you can have until midnight. How about that? All right, so this way you've got until Wednesday at midnight. That should be plenty of time. Now, also, what I'm going to do is, last assignment, please have the chapter 8 problem set ready by Monday. Usually, this will be Monday as usual. Next Monday is the 28th. At midnight is fine. And then that's it. As far as the chapter 9 and 10 problem sets go, we'll review them, but you just won't have to hand them in. Okay, so if you're wondering about that, they'll be posted. But what we'll do next week is we'll wrap up whatever's left over from 9, we'll do 10. We'll do the 2 problem sets, and then we'll do the review of the final exam, which will be, like I said, shorter than this one. It didn't work out. Wasn't able to split it up equally into 2 halves. There's more math, there's more topics in the first midterm, the midterm rather. But I don't know, maybe I don't know how you look at it, but if the midterm is harder than the final, that actually might be a good thing because you'll have a better feel for where you stand. So, all right, anyway, so why don't we stop right here for a bit and have our break. And when we get back, we're going to have chapter 9 We'll get as far as we can. And I do want to point out with chapter 9, although it seems a little complex, the calculators will be enormously helpful with chapter 9. They can really make our lives a lot simpler. So we'll go through all the theory and all, but you'll see pretty quickly that once you start getting used to the calculators for this function, it's really not that complicated. It just takes a while to get used to it. And the same thing could really be said for chapter 10. So anyway, so let's stop for a bit. I'm sure you're worn out from all that reviewing, and we'll pick it up right here, and we'll just get as far as we can into chapter 9. So your job then is over the weekend, do the chapter 8 problem set. Let me make sure it's here. Oops. Oh boy, it's not there. I better put it there. And the midterm, okay? Hold on, before I forget. Well, all right, I'll take care of that later then. All right. So, all right, so let's stop for a bit, and I'll see you in a while, after we've had some very badly needed refreshments. All right. Okay. All right, so now we're going to go look at chapter 9. And okay, so I mentioned last time that this is our discussion about confidence intervals. So what is this idea of confidence intervals? It's a range of values which is assumed to contain the true value of a population parameter like the mean with a given level of confidence. All right, so let's say, for example, we construct a 95% confidence interval for the mean price of a gallon of gas in the US, and we come up with $2.99 up to $3.39. What this means is that we believe there's a 95% chance that the actual population mean price of gas is somewhere between $2.99 and $3.39. There's still, of course, a 5% chance that it will be outside of that range, but we're pretty confident that the true value of the mean is in that range somewhere. So we call this a confidence interval, specifically a 95% confidence interval, because that's what we think is the likelihood that the mean is actually in that range. Now, we can actually, by the way, we'll be able to construct any confidence interval we want. The most common choices are 90%, 95%, and 99. The choice that you make depends on how accurate this is going to need to be. In other words, it depends on what you're trying to prove, but how important it is to avoid any errors. So, by the way, because there's two numbers, we're going to define the 299 as the lower limit of our interval, and 339 will be known as the upper limit of the interval. Now, here's a quick example of something you may have thought about in your own life. What if you want to determine the average length of time that it takes to get to school every day? So every day for a month, you write down the time that it takes to get to school, and you find out that the sample mean is 30 minutes, but you recognize that some days it took longer than that, and sometimes, or some days it took less time. So the 30 minutes is a good estimate of the average commuting time, but it's kind of incomplete because it doesn't give us any sense of how much longer it might take on a bad day or how much quicker it could be on a good day. So we sit down and use the techniques from this chapter, and we determine that 95% of the time, the commuting time turned out to be somewhere between 25 and 35 minutes. In other words, the vast majority of the time, while on average it's 30 minutes, it can be as little as 25 or as much as 35. And that still leaves room for the extreme outcomes, like that day when there was construction going on and it took you 45 minutes, or that other day where there was a holiday going on and so you got here to school in 15 minutes, but most of the time it was somewhere between 25 and 35 minutes. So the 30 minutes, our estimate of the sample mean, is often referred to in statistics as a point estimate, which simply means it is a single value. Okay, the word point here means that it is a single value. The interval, on the other hand, from 25 to 35 minutes is often referred to as an interval estimate. But specifically, when we attach a level of confidence to our interval, it becomes a confidence interval or interval estimate with a given degree of confidence. All right, so we're making a distinction here between two types of estimates. The single value, which is what we've done up to this point, is called a point estimate, and a range of values is referred to as an interval estimate. And when we attach a confidence level to it, it becomes a confidence interval. All right, so I think we get it. Now, let's jump ahead a little bit here. How do you construct a confidence interval? In other words, what exactly happened here? Where did we get these numbers from? Well, we always do it in the following way. We start out with a point estimate like the sample mean, and then we both add and subtract what we will call a margin of error. And that represents how uncertain this point estimate really is. Now, later on, we'll see that there's a specific formula for the margin of error, but just think in terms now of general big picture things. The point estimate plus or minus some margin of error is what we need to calculate a confidence interval. And in this specific case where you're looking at the confidence interval for a population mean, the point estimate is, of course, X bar. Okay, so in other words, if we're looking at the confidence interval for a population mean, then we have X bar plus and minus the margin of error. Now, later on in this chapter, we'll do this for a population proportion, and we'll see that X bar is replaced with the sample proportion. But either way, you'll have an estimate plus or minus a margin of error. Now, if you take your mind back to the example we had for the student who's commuting, we noticed that the average commuting time was 30 minutes, but the confidence interval was 25 to 35 minutes. And how did we get that? Well, if you notice, the 25 is 30 minus 5, and 35 is 30 plus 5. Okay, so in other words, in this case, we had a sample estimate or point estimate of 30. The lower limit of this interval is 30 minus 5. The upper limit is 30 plus 5. So therefore, our margin of error must be 5 minutes. All right, and so you can see very easily that 30 is in the center of this interval, and the lower limit is 5 below, and the upper limit is 5 above. Therefore, the margin of error must be 5 minutes. All right, so what we'd like to do now is some actual calculations. It turns out that if we want to construct a confidence interval for the population mean, there are two cases that we will run into. And they depend on whether or not we know the value of the population standard deviation. If we do, we can continue to use the standard normal distribution to construct our confidence interval. If we don't, we have to use something different, which we'll introduce in this chapter. But for now, let's focus on the first case where we know the population standard deviation, and that allows us to use the standard normal distribution. You can tell because there's a Z in here. The Z represents a Z-score. Now, everything else in here you should probably recognize, except possibly this term. And this is the Greek letter alpha. What does it mean? Well, we're going to find out in a second. So based on our discussion earlier, the confidence interval, remember, is the point estimate plus or minus a margin of error. So what that means is that this entire expression on the right is the margin of error for this confidence interval. X bar is the point estimate. Okay, now the only thing we have to do here is figure out what this alpha means and we'll be all set. All right, so this is our margin of error. The Z by itself is called a critical value or Z-score. The sigma over the square root of n is called the standard error of X bar. And of course, just as a quick reminder, sigma would be the population standard deviation. I don't think you've forgotten that, but I just want to mention it again. Sigma represents the population standard deviation. Now, this is the new part. Alpha is referred to as the level of significance. And we'll see that again in chapter 10, by the way. But how does that relate to a confidence interval? Because of the following definitions, the value of 1 minus alpha is really what we're interested in. That number is called a confidence coefficient. And if you multiply that by 100, it becomes known as the confidence level. All right, so again, how does this relate to our confidence interval? Well, this is something that we choose before we start the calculations. So just as a quick example, what if we're interested in calculating a 95% confidence interval? Well, let's look at the numbers. That implies that 100 times 1 minus alpha is 95. And if you do the algebra, you'll see that the alpha is 0.05. So for a 95% confidence interval, alpha is 5% or 0.05. All right, now both of these actually mean the same thing. In other words, if I tell you that I'm constructing a 95% confidence interval, or if I tell you that alpha is 5%, it means the same thing. They're basically alternative ways of expressing the same information. But there's also, like I said before, a couple of other possibilities we might run into. Let's say, for example, you're really interested in doing a 90% confidence interval. In that case, alpha is 10% or 0.10. And of course, if it's 99%, and these are the only three that you're most likely to run into in practice. There could be others too, but these are by far the most important ones. For 99% confidence interval, alpha would, of course, therefore be 1% or 0.01. All right. Now, when you go back, let's go back and look at this formula for the margin of error for a second. Now that we kind of have a feel for what alpha is, we have to note here that when we wrote this z-score or critical value, the subscript is alpha over 2. So what we have to do is figure out what exactly this number is telling us. All right, so let's draw a little picture here. What if we're interested in constructing a 99% confidence interval? That means we are going to have two z-scores. We'll have, here's the center, which is 0. This is z alpha over 2. And this is negative z alpha over 2. You can see here that with a 99% confidence interval, alpha is 0.01, or you can also say that alpha over 2 is 0.005. So what that means is that the areas in these two tails are each equal to 0.005. So the question is, what z-score is associated with these two tail areas? Because what we're actually saying here is that the probability that z, well, actually, it turns out I've already shown it. It's down here in the bottom. The z-score, we'll see how we figured this out in a minute, turns out to be 2.576. And I'll show you in a second how to do this on your calculator. That implies, by the way, due to the symmetry of the curve, that this z-score is negative 2.576. So this is a z-score, and what this means is that the probability that z is greater than or equal to this value is 0.05. It also implies that the probability of z is less than or equal to negative 2.576 is also 0.005. So where did I get this 2.576? Well, the calculator is going to help us with this. What we're going to do is use it to do, in effect, a reverse probability. Normally what happens is, or up to this point, what we've been typically doing is, for example, if I wanted to know the probability that z is less than or equal to 1, and it turns out to be 0.8413. So what we've been given is a z-score, and we calculate the probability. What we're doing now is working this backwards. We're saying, here's a probability. Now let's say it's 0.9772. So what we're trying to do is find out, what is the z-score such that probability that z is below that z-score is 0.9772. All right, how do we do this? We go to the calculator, we go to the menu we've had many times before, second vars, but now we're picking number 3, INV norm. Now, for the case that I just had a minute ago, where the tail areas are each 0.005, how did I find those z-scores? I actually did this. If the area in the right tail is 0.005, everything below that, all the way down to negative infinity, must have an area of 0.995. So this function, by the way, INV norm stands for inverse normal distribution. And so what I'm telling it is an area, and using the assumed mean of 0 and standard deviation of 1, and it will show up with 2.576. And it's interestingly enough, now if I change that to area 0.005, same mean, same standard deviation, the area will be listed, or the z-score will be negative 2.576 because of the symmetry of the distribution. So this upper one is 2.576, and this lower one is negative 2.576. And so what that basically means is that the area in the tails is 0.005. These are the corresponding z-scores. All right. That's for a 99% confidence interval. What about the others? What about 95? Let's find out. Okay. 95% means there's 2.5% in either tail. And so what I have to do is go to my INV norm function, and here's how I have to approach it. If the right tail area is 0.025, the rest of the distribution has an area of 0.975. So what I'm going to do is use INV norm of 0.975. And it comes up with 1.96. which means this one is negative 1.96. All right. Now let's do the same thing again. And by the way, here's the actual steps involved. Second vars, INV norm, 975. Leave these at 0 and 1, and there's your final answer. That's your z-score. All right. Then finally, what about 90%? What do we do now? That implies that 5% is in either tell so that means that the area below this first z-score is 0.95. And if you type in INV norm 1.95, you'll get 1.645. So that means this z-score is 1.645. This one is negative 1.645. Okay, and I got this by using the INV norm. All right. Now, that to me is really the only tricky part with these calculations. The rest, you're pretty much just plugging in the numbers that you were given in the problem. This is the challenge right here. But once you've done this, you can actually memorize these because they're the same ones over and over again. So in other words, once you figured out what the proper z-score is for 90%, you never have to do it again. You might want to write it down or memorize it because it'll never change. All right, so let's take a look at our first example. So a hedge fund contains a portfolio consisting of 500 stocks. The returns among these stocks are normal. The standard deviation is 0.20. Now, this is the population standard deviation. And the sample that we're choosing has 10 stocks in it, and the sample mean is 8%. By the way, it does mention the population size, but it's not really needed in these calculations, so you don't have to worry about that. So we're going to take this information and calculate 3 different confidence intervals for the mean of the population with 3 different confidence levels, which are 90, 95, and 99. So we'll get some practice with all 3 of them. All right, so we'll start with the 90%. And of course, the first step is usually to calculate the appropriate z-score, which we just did, but you can see it here again. If you go to INV norm of 0.95, you'll get 1.645. If you did INV norm with 0.05, you would just get negative 1.645. But you really only need one of them. So now we can plug everything into our formula. Look at how easy this is. So you've got n, you've got sigma, you've got x bar, now you've got z. So you plug in the numbers. Now down here, this is your point estimate, or x bar. And this is your margin of error. So we've got the mean. We know that the mean is 8%. So we're adding and subtracting the margin of error of 10.4%. So what this is telling us is that we are 95% confident that the true population mean is in this interval somewhere between a loss of 2.4% and a gain of 18.4%. So this is our 90% confidence interval. All right. Now, in order to construct the other two confidence intervals, 95 and 99, only this changes. The rest of the information is the same. All right, so you'll see that in the next case. In part B, we're doing 95% confidence interval. So all I need to do is change the confidence, the z-score. All right, so this is 95%. And earlier we looked up the correct z-score and turned out to be 1.96. So you can see the point estimate hasn't changed. It's the margin of error that's different. And this is our 95% confidence interval. And if you notice, remember the last one, I'll just have a quick reminder here. 90% was between negative 0.024 and 0.184. So what happened here, if you notice, the range of values is wider. The interval is bigger than it was before with only 90%. We're allowing more possible values here in order to increase our confidence that we really have the true mean somewhere in this interval. So whenever I raise the confidence level, the interval will get bigger and bigger because I need to allow for more possible values. So when we go to 99%, you'll see that the interval will get a little bit bigger, as will the margin of error. Okay, the point estimate never changes. All right, here we go. So here's 99%. And the z-score, as we saw earlier, is 2.576. So that's going to change this. The margin of error will get even bigger. And this is our margin of error. All right, and you see how wide the interval has gotten now. It's really getting pretty big. It includes everything from negative 8.3% all the way up to 24.3%. So this is our 99% confidence interval. Okay. Well, you'll be here with all of that being said, you'll be relieved to hear that a lot of that work can be done directly with the calculators. The calculators can really speed things up with these types of situations, and they'll save you the trouble of calculating the z-scores yourself. What you mainly have to focus on is making sure that you've chosen the correct calculator function. So when you're calculating confidence intervals for the population mean, where the sigma is known, then you'll use the following steps. So you'll go to stat tests, and which one of these do you pick? You're going to pick number 7, Z interval. All right, go down to number 7, Z interval, and look what it does. Oh, one more thing. When you get there, there's two more menus, data or stats. Make sure you use stats. So then you plug in the numbers. You know, remember the standard deviation was 20%. X bar was 8%. Sample size was 10. C level obviously means confidence level. So hit that button and then calculate. And you'll notice that's exactly the same as what we did before when we did it by hand. Well, that's good to know. So look how easy that was. Huh. So all that work we did before can be replaced with this wonderful calculator. Well, I'm glad to hear that. Then when we change this to the 95% confidence level, remember the interval gets a little wider. And so all you have to change is down here, 95% confidence level. That's it. And so look what happens to the interval as we predict or remember from before, it gets a little bit wider. Okay, see how easy that is? And then 99%. Just change this at the bottom. Whoops. And you'll have your answer. And it'll be exactly the same as what you did earlier. There might be some very trivial rounding differences, but it is the exact same number or set of numbers. All right, so all those details are right here in the slides. So go get them and take a look. And when we're doing these problems, I don't know, I think especially given how much little time we have left, you might want to think about using the stat test menu, because doing it by hand is fine as far as it goes, but you know, this is still a fairly complicated process, and it's nice to know that at the very least you can use this to back up your results. But this is what it was doing. In other words, it was just basically preventing you from having to go through all these steps, but it did exactly what we did here. It created the point estimate, it created a margin of error, it looked up the z-score for you, and then it plugged them in and came up with this result. All right, now we said earlier that there's only two basic cases we need to consider when we're trying to come up with a confidence interval for the population mean. In the first case, the population standard deviation was known. Right there. So obviously the second case tells us what to do when the population standard deviation is not known. So that's it. That's all we have to choose from. So now, and by the way, what we're about to do is the much more common case. You know, in practice, you don't often know this population standard deviation. So the next case is really the more important of the two. So what is that second case? Where are we? Sigma is unknown. And if you look at this carefully, you'll see there's some important differences. Number one, we've replaced sigma with S. But the most important detail is right here. What is this? Oh, this is something new. We're about to introduce a brand new probability distribution. Yes. So all of a sudden, we'll have another one to choose from. And this one, as you can clearly see, is called the t distribution. So let's take a quick look at the t distribution. We have to understand how it works, how it's different from the standard normal, and how it's the same, because they do have a lot in common with each other. And the t distribution also has a very interesting history of its own. Oh, and sometimes you see it called the student's t distribution. It's called the t or the student's t. We'll see why in a few minutes. And it has the alpha over 2. This is something new. we're going to see in a few minutes that this piece up here is referred to as degrees of freedom, which we'll explain in a few minutes. Okay, so this is taking the place of the standard normal distribution. Okay. So the T distribution was created in the early 20th century by W.S. Gossett, William Gossett, and he published this research in a very famous econometrics journal, but he wanted to remain anonymous, and I'll tell you why in a minute. So he wrote, we don't know why, but he decided to write it with the name student. So the paper appears in this journal, and it just says student instead of W.S. Gossett. So for the longest time, nobody realized that he was the author of this paper. So it came to be known as the student's T distribution. Gossett chose to call it the T distribution, but because his name was listed as student, the public often refers to it as the student's T distribution. Even though we know that it was Gossett now, for whatever reason, nobody ever calls it the Gossett T distribution. It's just called the student T distribution. Now, Gossett was actually the head of the quality control at the Guinness Brewing Company in Dublin in the early 20th century. And the reason why he had to publish his paper anonymously is because when he got to his job, his immediate predecessor had apparently been involved with industrial espionage. He was trying to sell trade secrets to other companies for money, of course. So when Gossett arrives at this position, he was told that he can publish his research if he wants to, but not using his own name, because they didn't want anyone to know what they were actually doing at Guinness. In other words, it was meant to be proprietary information. So he was able to publish it, but he couldn't actually use his name on the paper, so he chose the name student. And the purpose of the T distribution is to explain the properties or the statistical properties of X bar, or the sample mean, when we have small samples. Now, you might remember from our discussion about the central limit theorem, the central limit theorem guarantees us that if the underlying population is normal, then our X bar is normal. If not, as long as the sample size is above 30, we can still justify using the normal distribution for X bar. What happens though if n is the sample size is less than 30? Then one of the ways we can get around that problem is to use the T distribution instead of the standard normal. So the standard normal is used for cases that are justified by the central limit theorem, but the T distribution is used for the cases where we cannot use the normal distribution. Because what happens is the properties of the sampling distribution of X bar become very different when we have small samples. So we have to have a way of, we have to use something else instead of the standard normal if we have small samples. And that's what Gossett set out to do. He realized that, according to the central limit theorem, we can always use the normal distribution with large samples. What do we do if there are small samples? Nobody had ever written about that. So Gossett said, you know what? I'm going to take a shot at this. I'm going to demonstrate a new distribution that we can use when the conditions of the central limit theorem don't hold. And of course, it's been used ever since. It turned out to be so successful that statisticians have used it ever since. So Gossett turns out to be a major figure in the history of statistics, even though he technically wasn't a statistician. But as a quality control specialist, his job was to make sure that the beer that they were selling was of sufficiently high quality before they actually, sold it to the public. And of course, any process where products are being made, quality control is an extremely important part of it, because they have to make sure that everything is working just fine when they sell products to the public. All right. So with that background, let's take a look at the actual properties of this t-distribution. Now, I do have some graphs of it in here that I generated with a computer program. But just in general, I just want you to see that the t-distribution, like the normal, is continuous. It has a mean of 0, and it has the shape of a bell-shaped curve. So in a lot of ways, it very closely resembles the standard normal distribution. It's continuous, it's symmetrical about the mean is 0, and it has our very well-known bell-shaped curve. So far it sounds like it's exactly the same as the standard normal. What's different? That's the big difference. That's the key detail. The t-distribution is more spread out than the standard normal, meaning that the tails are bigger and the area in the center is smaller. So I know it's hard for you to visualize that now, but I have a couple of graphs that should make this much more clear. So for the most part, it's very similar. Again, the t-distribution is continuous, symmetrical about the mean, has a mean of 0, and it is a bell-shaped curve, but it's more spread out. That's really the most important detail. Also, this is something that's unique to the t-distribution. Remember, we talked about parameters the other day. The binomial, remember, has the parameters n and pi and Poisson, lambda. These are the values that uniquely characterize that distribution. The t-distribution only has one parameter, which we call degrees of freedom, which is usually designated by this new Greek letter that we're about to see. It looks like a fancy V, but this is the Greek letter nu. And that's the only parameter for the t-distribution. If we know that, we know everything we need to know about the t-distribution. But if you remember us saying that with a binomial distribution, as n gets larger, the binomial distribution gets closer to the normal, or the standard normal, I should say. The same thing is happening here. As nu increases, the t-distribution converges to, meaning it gets closer to, the standard normal distribution. All right, so I think it's time to look at some graphs so you can really see what's going on here. So we start out with this graph. I've got two curves. One is green and one is blue. All right. So, all right, let me give you a second to catch up with this. And then this way, I'm hoping you can see exactly how these two are different from each other. All right, so this green curve, this is the standard normal. The blue one is the t-distribution with 5 degrees of freedom. Now, if you look at it very, very carefully, you'll see the blue curve isn't quite as tall. It is centered at 0. So they're both centered at 0. They both have a mean of 0. They're both bell-shaped curves, and they're both symmetrical about the mean. What's different, though, is that the blue curve has more area in the tails, and less area in the center. In other words, if you look at this range here, for example, the green curve is slightly wider than the blue curve. So the blue curve, the T, has less area in the center or the middle. So basically, in a nutshell, with the T distribution, extreme outcomes or extreme values are more likely than with the standard normal. All right, more air in the tails, less air in the middle. So you're more likely to get extremely large and small values than you would get with the standard normal. Well, let's see what happens now when I increase the degrees of freedom from 5 to 30. All right. So right now the degrees of freedom is pretty low. That's 5. So you can see the difference between the two fairly clearly. But as I said before, as the degrees of freedom increases, the two will get closer to each other. In fact, I think you'll find it hard to tell them apart. All right. Now look at that. You can't even see the difference. It's so faint. It's so vague. Here, this is T with 30 degrees of freedom. And the green, which is just barely visible down here, is the standard normal. So once we get to this point, the two distributions are virtually identical to each other. So in other words, the T distribution is very useful with a small number of degrees of freedom. After that, not so much. After that, the two are more or less interchangeable with each other. So with Gosset, the idea here was that we want to test our product, but we don't want to use it all up in the process of testing it. So we would like to have the ability to draw conclusions from small samples rather than large samples. And so that's why he invented this. Now, these are the moments that we need to know for the T. Remember, all of these distributions have their own special formulas for the moments. So for the T distribution with new degrees of freedom, the mean is just 0. All right, we already saw that. The variance, though, as you can see, is clearly a function of the degrees of freedom. Also, if you note here, as a technical note, none of this works. Nu has to be at least 2, otherwise we have an undefined variance. And so you can probably imagine what the standard deviation looks like. It's just the square root of that variance, okay? So the standard deviation is here. It's the square root. All right, so what's coming up next is we're going to do some confidence intervals with the T distribution. First, we'll do it the long way using the full formula. But by the way, we can look at these up. These values can be found in a table. So there's a new table for this, or with the function in the calculator. It's called INVT. So we're going to introduce that one on Monday. Now, remember, Monday, we're starting an hour early. So we'll do that, and then we'll do the calculators, the full-blown calculator examples. And then when we're done with that, we're going to do the same thing for the population proportion. Okay, so by the time we're done, we'll have 2 techniques for confidence intervals for the population mean and 1 technique for the population proportion. Okay, when that's done, we can dive into chapter 10, and then we can wrap up the course, I guess, with some final exam reviewing. All right, anyway, unfortunately, we're pretty much out of time, so I think we better stop right here. It's probably getting to be a bit too much anyway. There's a lot of technical details here, but we'll get through it. So I'll see you all next Monday, and don't forget to work on those midterms. And, oh, by the way, because we didn't get through the whole chapter, the final assignment for next week on Monday will be just the chapter 8 problem set. How about that? Anything beyond that would just be too much. So you just have to do the chapter 8 problem set, which I'll be posting this afternoon, and then we'll be all set with assignments. All right. So I'll see you all next time. All right. Bye, everyone.